All right, so mic on. So I thought we'd have a little bit of fun today. See something that you don't normally see in CS1. Gave you kind of a thought-provoking lab yesterday. How many of you managed to get through the lab okay? All right, so there's stuff in the lab that I think is really interesting, and it fits in with this last topic that I want to cover in class. So let's first cover the details here. Don't forget homework 3 is due midnight on Friday. You will have one last question of the day, but it's a special edition in the sense that if you don't do it, it doesn't matter. So this question of the day, there were 16 of them. We're dropping 5, I believe, and counting your top 11 scores. If you do this one and you get it right, we'll count it. If you don't do it, we're not raising the number of questions of the day you have to do. So it's basically a freebie. It's a little more challenging than some of the other ones, but it's probably worth doing if you have a chance. How many are done with homework 3? Some of you are done already. Okay, good. The TAs tell me they won't be done grading homework 2 until the weekend, and so the estimated grades will have to wait till Monday morning. It's the best I can do if I'm going to include homework 2 grades in with the estimates. Final exam next week. People with SDS accommodations, you'll sign up in the usual way. I'll set that up later today so you can go set your time. Anybody with special circumstances that make it difficult to be at the exam, you need to talk to me sooner rather than later. And I know a few of you have written me, and I'll deal with that later today as well. Okay, let's look at Lab 12. So in Lab 12, there were 2 parts to Lab 12. One part which was really pretty straightforward. That part is this stupid function xyz, which doesn't really mean anything. And it's basically a ripoff of the Fibonacci sequence function that computes Fibonacci numbers. I just made a change to the recursive formula, or to the recurrence relation, if you like. This is my solution. I think most of you would have gotten this and probably would have written something very similar. Basically, if n is 0 or 1, then you return 1. Otherwise, you write out the recurrence in the recursive statement. All of this fits because we have a base case and we have a recursive step, and each recursive call in the recursive step makes progress towards the base case, provided n starts out as a positive integer, which is what you were told. So an interesting question with this is, how many times does xyz invoke itself when you call xyz as a function of n? Obviously, the number of times depends on what the value n is. And in fact, the number of times it invokes itself is intimately related with the runtime analysis of this function. So if you think back to when we did algorithmic analysis, I introduced this. There were 5 rules for algorithmic analysis. And I told you that the rule 5, I think it was, for recursive functions is that you multiply the number of invocations times the cost of each invocation. And here the cost of each invocation is just some arithmetic in the recursive step and just a lookup in the base case. So the cost of each invocation is clearly constant time. You do a constant amount of work in each invocation. So the runtime of this function overall pretty much just depends on how many times you call it. So I give you a value n, and we need to come up with a description of how many invocations of xyz it takes to compute n. And the answer is it's a little bit complicated to do this in closed form. But we can do some other things. We know it calls itself a lot, right? Because every time I call xyz of n minus 1, well, that implies I'm going to call n minus 2, and also n minus 3, because this expands into something where I have n minus 2 and n minus 3 there, and so on down the line. So I have this recursive expansion that clearly makes a lot of function invocations. So solving for it exactly what this recurrence relation is, we'll wait until you get to algorithms class, so CS 3330. But we can do this pretty easily by making a new version of the function xyz. And so that's what we're going to do right away. This is what my new function looks like. It's an invocation counting version. It looks like this. This is exactly the same function, except there's this optional parameter c, which is set to 0. And every time I enter the function, I add 1 to c. And then this is all the same, but instead of returning 1, I return a tuple with the count and 1. And here in the return, I have the tuple with a count and 3 times R1 and R2. So this is result 1, which is the first recurrence, and result 2, which is the second recurrence. Since I return 2 values, I update C each time. So at the end of the day, when I invoke this function, just as if I were invoking xyzn, I don't have to give C because it defaults to 0. I will get back a tuple, which is the value of the xyz function, and also how many times it invoked itself. And if I try this, I try it with n equals 1, I get back that it invoked itself 1 time, and the answer is 1. With 2, I find out that it invoked itself 3 times, and the answer is 2. And if I do it for 10, it invokes itself 177 times, and the answer is 4181. And I can check these answers against my generic xyz function that I implemented first, and in fact, 4181 is what I get for 10. So I know that I did the implementation correctly. Everybody with me so far? It's really straightforward. Okay, so the rate of growth here is clearly more than linear. From 1 to 3 to 177 over 10. Clearly there's some sort of upward concavity here in the function of growth rate. Precisely how much more than linear is the question. So I'm going to ask you to accept this on faith. In fact, it's exponential. Now, it could be quadratic, because that also looks concave up, but this is in fact exponential, which means it has a very fast rate of growth. And you can find this out by using the timer function I gave you and plotting the time returned to compute xyzn, from 1 to 20. You get that really nice exponential shape. It's very clear. But the insight here, behind this whole memoization idea, is if somehow I could just remember the solution for a particular n, when I get asked it again, I would just feed back the solution that I had stored away. And this remembering is where the term memoization comes from. So a little personal note, this word is a generic word used for functions that do this kind of recording. It was coined by a guy named Donald Mickey. Donald Mickey died 15, 20, maybe 20 years ago. I actually had him for a class when I was an undergraduate and also as a graduate student. He was interesting because he had worked with Turing at Bletchley Park. Do you know what Bletchley Park is? We talked about this, I think, early lectures. Bletchley Park was the code-breaking operation in World War II, where Alan Turing, the father of computer science, so to speak, and many other mathematicians broke the German Enigma codes. So Donald had been there in World War II, and then he became a CS professor, and later in life he moved to the University of Illinois, where I was a student, and I had classes with him. He was fairly old then. Good Lord, he must have been in his 70s. I'm 65 now, so he doesn't seem that old anymore. But he seemed old to me at the time, so I must be ancient to you. But he certainly seemed old to me. And he's also quite absent-minded, and he wore tweeds. It was kind of typical English professor. And his wife would accompany him to his lectures because he would get stuck. He would forget where he was. She would sit in the back row, and she would yell out the next thing he was supposed to cover, and then he would pick up from there. So he was a really eccentric guy, but who made interesting contributions to computer science. One of them is this word is the word he coined. So we still use memoization. Okay, so let's take a look at the second part of the lab, which is the memoized version of XYZ. And this is actually, I gave you enough, I think, to make it not too hard to implement. So here's my solution. I suggested you use try and accept, which is a pretty reasonable thing to use with the dictionary. The key thing is that the signature contains this dictionary M with a default value that corresponds to the base case of the recursion. See how elegant it actually is, right? Instead of having an if statement that says, if this is in the dictionary, if n is 0 or 1, return 1, just put it in the dictionary and prime the dictionary with those values and try it. If you're trying a small value of n the first time, then m of n will be one of these, and you just return it. No muss, no fuss. On the other hand, if the value of n is not in the dictionary, this try will fail because you will get a key not found error in the dictionary. The accept will kick in, which will invoke XYZ memo recursively. and set the dictionary to remember what the solution is, and then just return that solution. Right? So it's nothing to this. This is a very simple function to memorize. I've just altered it so that I'm going to make essentially this function driven by the dictionary of solutions to the function. In the limit, right, if you think about this, there are a lot of functions that you can write that basically are just big lookup tables. If you had infinite amounts of memory, you could write a perfectly reasonable function for Fibonacci numbers that goes up to 100 million or whatever the largest Fibonacci number you care about is, that just has a value of the n and its Fibonacci number. And you could just build a table and that would be your function. The problem with that, of course, is this table gets really big. And the bigger the table, the slower it is to index, the more memory your computer needs. It's not an ideal solution, but it does illustrate that there's a trade-off between computing something, computing it, and looking it up. And that trade-off is sort of what we call a space-time trade-off, space to store versus time to compute. So this is an example of using that trade-off dynamically. Let's take a look at how this works. So I'm going to use the timer function I gave you. I'm going to use my original XYZ function with a parameter 10. I get back to 4181, so I know it's working. And this is a elapsed time in seconds. And as I increase the size, you can see the time goes from like 1 times 10 to the minus 4th to 7 times 10 to the minus 3 to 3 times 10 to the minus 1. It's clearly growing, as we now know, exponentially. So it's getting slower because as the number gets bigger, you're doing more and more computation, and so things slow down. In contrast, when I use the XYZ memo function for 30, I'm back at 1 times 10 to the minus 4 here, whereas the regular XYZ function was 1,000 times slower, actually 3,000 times slower. So this XYZ memo function on the same parameter is much faster, yet it returns exactly the same value. In addition, if I just invoke it again, second time, not only was it faster the first time, but it gets even faster the second time. Right? So two things going on here. One is it computes the function result more quickly, and the second one is it seems that quickness persists. It becomes faster with time. So two factors. One of them we'll call the within invocation speedup. That's what we saw here from XYZ 30 taking 0.35 seconds to XYZ memo 30 taking less than 1 times 10 to the minus 4, or less than 2 times 10 to the minus 4 seconds. So that 3,000 times speed up. And the second one we'll call a cross invocation speed up, which occurred between this invocation and this invocation. So two forms of speed up here. So let's take a look at the first form, the within invocation speed up. Why is XYZ memo so much faster than the function XYZ? And to answer that question, it's helpful to look at the tree of function calls for this XYZ memo. Now, remember, the XYZ function is a ripoff of the Fibonacci function, so the calling tree will look exactly like Fibonacci, and this is an example of what it looks like. This says when you invoke Fibonacci, or in our case XYZ, with a value of 6, you need to compute Fibonacci with a value of 5 and Fibonacci with a value of 4. And to compute Fibonacci with a value of 5, you need to compute Fibonacci with a value of 4 and one with 3, and that requires 3 and 2, which requires 2 and 1, and 2 and 1, and 2 and 1, and 3 and 2, and so on. All right? So when you look at this tree of function calls, an invocation of Fibonacci 6 recursively invokes these two calls to Fibonacci, which in turn recursively invoke the subsequent calls to Fibonacci. Does everybody see the pattern here? All right. Now, what you should notice, of course, is that, for example, Fibonacci 2, 1, 2, 3, 4, 5, is actually called 5 times. So every time it's called, I do the calculation for Fibonacci 2, or in our case, XYZ 2. If I could just somehow remember what the value was the first time I invoked that, the first time I call Fibonacci 2, just store away the value of Fibonacci 2, then 4 of those invocations are redundant. Right? Just remember that invocation and then and return that value instead of recomputing it. So the trade-off here is, do I remember it or do I recompute it? And the whole point behind memorization is that we build a cache that memorizes, that remembers the values that you returned before, and for deterministic functions, functions where the answer will always be the same if the inputs are the same, you can make the function speed up. Okay? Of course, this doesn't work if XYZ were non-deterministic. If it had some randomness in it, then this would not help us, right? Because every answer would be different, and this would only remember one answer. So this is, have you seen this word before, cache? Everybody familiar with this word? It's like your gallbladder, right? Your gallbladder is a cache for bile. It lets you store something away that you use later. That's exactly what we're doing here. So this is a classic technique in computing that trades space, in this case memory, against time, in this case saved recomputation. And managed judiciously, this is a great thing. Right? You can go overboard, but it can actually help you out quite a lot. So that's the within invocation speed up we saw. But there's also an across invocation speed up that's kind of interesting. And let me show you this series of inputs to make this one clear. So I'm going to start X as being a value for a dictionary with the same dictionary that I had in the invocation of my XYZ memo, right? These are the base cases. XYZ of 0 is 1, XYZ of 1 is 1. Those are the base cases of my function. And I'm going to invoke XYZ memo with 10, but remember, the first time I did this, I left the optional argument out, and I let it default to whatever the default value was for that optional argument. Here I'm going to supply X as that optional argument. So this is, in fact, a copy of what I had in the definition for XYZ memo. Now, once I invoke XYZ memo here, if I ask what the value of X is, I see that X's value has changed. And what it contains now is that lookup table. It started with what I had before, but now every invocation of n has its, right up to 10, has its concomitant value for XYZ associated with it. And what's more, X in the global context has changed. So let's think about what's going on here. This is a structure, this dictionary, which is, remember lecture 1, it's a mutable structure. And that and when you pass a mutable structure to a function, you're essentially not passing this, you're passing a reference to this structure. So there is in memory somewhere a dictionary that I've called X that contains 0 and 1. And when I invoke XYZ memo, I'm telling XYZ memo, here's my dictionary, use this. So XYZ memo, as it operates recursively, uses my X dictionary to store its intermediate results. But when XYZ memo terminates, the changes to X are permanent. They're lasting, right? They in a sense, they're not passed back as a value, but I've made mutations to the function, to the dictionary. Yes?
Why don't they just go back to the default value?
Why don't they go back to the default value?
You're not passing n back into the...
I'm going to get to that in just a second. It's a good question. Hang on a second and see if this answers your question. So we're in agreement that if I give you this function here, X, dictionary here, X, you understand how this invocation works. Your question is, what happens when I don't give the X, right? Is that right? Yeah, okay. So hang on just a second. So do we all agree that if I pass my own dictionary in here, I expect these changes to be long-lasting? Everybody agrees with that? But here's the thing. When I define my function, that default value is evaluated at definition time. So let's go back to our XYZ definition. When does this dictionary get built from its written description into a dictionary object that is assigned as the default value of n? And the answer is, that happens at definition time, not at invocation time. So when I define this function, the default value of m is set as part of the function definition. This is actually a dictionary structure that is stored with the function definition. It's one mutable dictionary object. And so, when I invoke my XYZ memo function, even without passing it the x value, that m, which was evaluated at definition time with the 0, 1 in it, is the thing that's being altered. And if I call XYZ memo again without passing a second argument, it gets the altered dictionary as its value. That answer your question? So this is cool because it means that I define my function with this default argument, and the default argument itself is organic. It changes as I use the function over time. So that gives me the across trial speed up. With first time I invoke XYZ memo of 10, I'm going to modify that default m dictionary, and the next time I call it, my answer is already in the dictionary, I just return it, which accounted for that second speed up across invocations. So XYZ memo continues to grow m and increase speed for larger values of n as I use it. It gets faster. Every time I use a value of n that I haven't seen before, I'll compute that new value, taking advantage of the within invocation speed up, storing the value in m, and the next time I go to a number that large, I'll already have the answer. Isn't that cool? I mean, come on, it's cool, right? Yes? Yeah, it's cool, right? It's really cool. Now, of course, there's a trade-off. The trade-off is that m is always going to continue to grow, and eventually, if you do this enough, you're going to find your machine is going to start to crawl because your Python image is going to have this giant m table that is hidden from you because you can't actually access it easily. You have to go dive into the function to get it. It's hidden from you, and yet it keeps growing and growing and growing and occupying space in your Python image. And we know that it's convenient to think of a computer as having infinite memory or infinite storage, but it really doesn't. Eventually, there's a real limit. The miracle of the last 50 years of computing is that limit keeps getting farther and farther away, more remote because there's more space, more memory, it's cheaper, bigger disks, we don't have to worry about it. But eventually, what we want to do grows with how much space I have available, and eventually you're going to hit that space limit, right? Now we can do these vast word embedding models for translating that, for interpreting natural language. Those things a few years ago wouldn't have fit on your disk. Now it's routine. So your greed for storage continues to grow, but storage itself is a finite resource. But I thought this was kind of a cool thing to see in CS1, right? These are sort of underlying principles of space and time trade-off, are things that programmers have to deal with and computer scientists have to deal with at all times. And this is a really stark kind of demonstration of how this works. Now, it is interesting, and you will get to this in 3820, Programming Language Concepts. This definition of XYZ memo, let me just one last indulgence, if you don't mind. This definition here is really, it's interesting, it's concise, it's brief, I mean, it's very elegant, but it's specific to XYZ, right? That is specific to the XY. For every function I want to memoize, I have to build its memoized version. Wouldn't it be great to write a function that takes as its argument a function and returns the memoized version of that function? So there was a generic memoization function that I could invoke on a function name. I could say memoize XYZ. It would return the definition of XYZ memo, which then I could use with impunity without having to rewrite my functions to be memoized. So that's kind of an interesting question. It's one of these kind of self-referential things. The issue is that it's easy enough to write an XYZ, a memoization function that will memorize arbitrary functions if you're only interested in retaining or caching the top level answer for n. It's another thing to be able to also memoize within the function to get that within function speed up. And so to do this in the right way is actually quite tricky also also from a language perspective or semantics perspective. So I didn't assign you that one, but I thought this would be kind of an interesting thing to see, and I'm glad we got a chance to do it. You may not be so glad as I am, but I thought it was cool. Okay, any questions on Lab 12? Anybody? All right, so today we're going to do the halting problem. So we talked about this already a little bit the other day. We talked about how some problems in computer science we say are tractable problems. Those are the ones that admit polynomial time solutions. And then some problems are intractable because when you have larger versions of the problem, it takes exponentially more time. We have seen that without the extra memory, our XYZ function is an example of an intractable problem. It is a problem that grows, whose solution time grows exponentially with the argument. It's actually, there are other solutions that don't, but the solution that we looked at is exponential time. There are other solutions that can be run in linear time that don't require memoization as well. But for that problem, it was an example of an exponential time solution. So sorting is a tractable problem, and traveling salesperson is an intractable problem. Unlike XYZ, which has a linear time solution even without memoization, traveling salesperson does not have a non-exponential time solution that we know of. So one of the giant problems in computer science, philosophical problems, is are those problems that don't have polynomial time solutions really hard, intrinsically hard, or is it that we just don't know how to solve them right yet? And odds are that they are intrinsically hard. If you can prove otherwise, or can prove that they are intrinsically hard or that they aren't, there's $1 million waiting for you as a cash prize for this challenge problem. It's an open problem. Okay, so let's talk about the third class of problems. And this is what I hope to finish today. This is a class of problems that are called undecidable problems. Undecidable problems are problems which you can provably say are not solvable by computer. There will be no solution to this problem. So in 1936, Alan Turing, we're just talking about him today. He was at Bletchley Park in Great Britain. He's the father of the discipline. Alan Turing introduced this notion of computability in his paper. And in his paper of 1936, he introduced the so-called Turing machine, which you'll see in either theory of computation or algorithms, which is a general theoretical model of how computers work. We talk about languages being Turing equivalent, meaning that they can compute everything that a Turing machine can compute. A Turing machine is a very simple thing that has, we'll go into it, but it's a very simple model of computation, and it's amazing how much it can do. It's just very slow at it. And he also introduced the halting problem as an example of this new kind of problem that I said can't be solved by computer. So here's what the halting problem is. The halting problem says determine, using an algorithm, whether an input program, like this one, will terminate for any input x. So let's look at this program. This is program P. It takes one argument x, and while x is greater than 1, we divide x by 2. Will this program terminate? Is there any x for which this program will not terminate? By terminate, I mean exit, stop running. Does it terminate? It's not a trick question. Of course it does, right? X gets smaller every time through that loop. Eventually, small is going to be less than 1, and the program terminates. So it's easy to see that for any x you throw at this program will terminate. What's hard is that this is not easy in the general case. In other words, it's easy because this program is trivial. If the program were slightly more complicated, it's not so easy. So here's an example of a more complicated program. While x is greater than 1, if x is even, divide x by 2. Otherwise, x is 3x plus 1. Now, if you think about this, in the previous incarnate problem, x got smaller every time through the loop. And we used the fact that x would get smaller every time through the loop, and that the loop terminates when x was small enough to claim that this was going to stop. But here, x gets smaller about half the time, and the other half the time, it gets larger. So for a particular value of x, I could just run this program. I could just say, So 7 is not even, so it becomes 22, then that becomes 11, then that becomes 34, 17, 52, so on and so forth. Eventually, I hit a power of 2 right there at 16. When I hit that power of 2, the program's on its way to termination. So I can show by running it that for a particular value of x that this program will stop. But I can't show, first of all, I can't show by running it that will stop for any x because there's infinitely many x's to test. And I don't have that much time. So I can't prove it for every x. Moreover, it's even hard for a particular value of x because I have no idea how long the program will run. And if I put in an x like 3,427 and it runs for a day and a half, is it safe to say it will not terminate? Do I just cut it off and say, okay, we're done, it doesn't terminate? What if it would have terminated 1 second later? You can't know the future, so you can't know. Not only can you not test all x's, but you can't even know when an x is taking a particularly long time here. You can't even know if it terminates then. You have to wait for it to end or be undetermined. So this is a logical conundrum, right? There's no way of knowing if this problem terminates, if this program terminates. So we're going to do a proof here. I'm going to wave my hands a bit, but this is really kind of interesting and worth seeing. We're going to do a proof to show that this halting problem, the problem of determining if a program will stop, has no algorithmic solution. In other words, there's no program that can solve this problem. The problem is well defined. Given a program, tell me if it will stop for any input. Easily defined. The spec is clear. You can't write that program. Nobody can. And I'm going to prove today that nobody can do it no matter how they try. And we're going to do this with a proof technique called reductio ad absurdum, which means in Latin reducing to the absurd, or proof by contradiction is what they call it in English. And it goes something like this. Assume something is true and show that it must lead to that assumption leads to some logically inconsistent results. And if that's the case, then the assumption that you made must in itself be flawed. In other words, the assumption that something was true cannot be true. And so that implies that that thing you assumed to be true was actually false. That's the general proof strategy. So what we're going to do is exactly that. We're going to assume that there is a program that solves the halting problem. And we're going to call that program, we're going to give it a name, H. It takes as input a program and a value, an input value for that program, and it outputs true or false. True if the program halts on that input, false if the program doesn't halt on that input. So this H program is a program that solves the halting problem. Does everybody see that? So P is an arbitrary program with its input X, and H says for that program and that input, the program halts. Or for that program and that input, the program does not halt. So it looks like this. Here's my little H program, subroutine if you like, my function H. It has two inputs. It has a program input and a value, an input to that program, a value that is the input to that program. And it either returns this doesn't halt or it does halt. So two outputs, true or false, doesn't halt or halts. We good? Questions? Okay. So two unusual things going on here. The first unusual thing is that you might balk a little bit at a program that takes a program as input. Right? So this program H has two inputs. One is a program P, and the other input is X, which is an input to the program P. Now I claim this seems a little weird, but we've seen this before. Compilers are an example of this. The autograder I use is an example of this. And I even showed you an example of this in class today. Anybody remember what it was? We had a program that was exactly like this today. Anybody? Oh, come on. Nobody? The timer function, right? I had a function called timer. The first argument of that function was a function. And the second argument to that function was the value that that function was being applied to. Right, so I said timer XYZ of 10. XYZ is a program, and 10 was the input to that program. It's exactly like this. So while it may seem to us that this may seem weird, especially to those of you who have done prior programming in Java or other imperative languages where functions are not first-class objects, this may seem weird. But in Python, it's routine. A function is just a data structure that you can pass around, and you can memorize it. You can write a function that memorizes it and changes that definition. So it's just data, just like a number is. So this may seem odd to you, but I think if you think about it, you should be comfortable with a program that takes a program as input. We're all good with that? The second weird thing that's going on here is that it's really easy to write a program that never stops. There's my example. We've all done it. Not intentionally, surely. But here's my example of an intentional attempt. I have a function forever. I say while true, and I don't do anything. So this program, guaranteed, will never stop. We all buy that? All right. So we're going to construct a new program, W. We're going to do this graphically. We're going to construct a new program, W, that actually takes as an input only one thing, a program, Q. So we're going to write we've already seen H, we've already seen P, now we're going to build a new program called W. W takes only one input, which is itself a program. Call that program Q. And W uses H as a subroutine. So it uses, remember I said, assume that you have a program H that does this. A program H that solves the halting problem. So here's my critical assumption. I've got this box. This works. I wrote it. Somebody wrote it. And it takes a program as P as an input and a value X as a value for P, and it returns doesn't halt or halt. This is my program W. It uses H as a subroutine. If H returns doesn't halt, then W halts. In other words, it exits, returns something. If H returns that it does halt, then I'm going to use my little subroutine while true pass and run forever. So W is a program that takes one input, uses that input both for P and for X, relies on my H program that I've said exists to have the behavior that actually is exactly the opposite behavior. Now a few odd things going on here as well. Looping forever is perfectly legitimate. We've just seen it. While true, pass. That is a legitimate use of looping. Q, the input to W, this thing, is a program that operates on a program. So you'll notice this funny bifurcation here. Q is a program, but when I pass Q to pass Q to H, it is both a program and data. So that implies that this H is now operating on a program P that itself operates on programs. Well, H is a program that operates on programs, just like timer. So it is okay to pass a program P that operates on programs as well. So it's not a big stretch to have P ask the question, does this program that operates on programs halt? Right? This is legitimate use. There's no difference between programs and data when you have first-class functions. So I haven't done anything unusual. When I built this W here, all I've done is assume that H exists, but the fact that Q can be both program and the input to that program, that's legitimate. The fact that I loop forever if H has a particular output, that's certainly legitimate. The fact that if H has a different output, I return, that's certainly legitimate. There's nothing wrong with my W function. There's nothing fishy. So now what happens if I take this W program and instead of some arbitrary program Q as input, I give it itself. So W, I'm going to operate on W. So I'm going to pass W as the input. W is now both the program and its input. And if H determines that W on itself halts, then W applied to itself will not halt. And if H returns that W on itself doesn't halt, then W applied to itself does halt. So this construction has exactly the opposite behavior. It's inconsistent, right? We've reached an inconsistency. W halts on W when my H program, which solves the halting problem, says that it shouldn't. And W doesn't halt on W, it loops forever, when my solution to the halting problem says that it should halt. So I've reached a logical inconsistency. And I've gotten there by assuming that H exists, and then everything else I've done is a legitimate sort of programmatic construct that we've seen in this class all the way around. So the only solution here is, if it says that that W terminates on W, so this is the inconsistency I just defined, that because W is legally constructed, the case is that the fault must be with H. In other words, my assumption that I have a program H is flawed. You cannot have such a program, because otherwise I would be able to build this kind of construct which is just inconsistent. So this is where mathematicians say QED, which means what you wanted me to demonstrate. And so this is a kind of a hand-wavy, informal, and pictorial proof of the undecidability of the halting problem. As it turns out, in theoretical computer science, when we are trying to make strong statements about undecidability, or strong statements about, optimal solutions in terms of runtime, these solutions, these arguments are often made by analogy to a problem that's already been proven to be, say, undecidable. Right? So in the case of runtime analysis, when we did sorting, I said we had a quadratic time, order n squared sorting algorithm, and I showed you quicksort, which in the average case was order n log n, and I mentioned that there was another sorting algorithm called heap sort, which is always n log n, and I think I believe I told you that n log n is the optimal runtime for sorting. You can't do it faster than n log n. We can prove in this mathematical kind of way that your heap sort algorithm is the optimal solution to sorting. You will never find an algorithm that is faster, no matter how hard you look. We're done. Those kinds of arguments of runtime, optimality, arguments about whether a problem is polynomial time decidable or non-deterministic polynomial time decidable, that's that gap between exponential time problems and polynomial time problems. Those arguments are often made by analogy to given a problem like satisfiability or like the halting problem, show that this problem I'm interested in shares those characteristics and must therefore be undecidable as well. So this proof is kind of like the foundational proof of a whole part of activity in theoretical computer science that says, hey, you've just posed a problem for which there is no computational solution. So we can stop right now trying to find a way to solve this problem and instead try to find a way around solving this problem so we don't need to solve it and we can still get work done. So this is why I wanted you to see this proof. CS is not, just this part, right? We spent a lot of time talking about implementation, a little bit of time talking about algorithms, very little time talking about design. But, I wanted you to get a feel for the kind of reasoning that goes on up here about different solution types. So halting problem, decidability, runtime analysis. This is exactly what you'll get in the rest of the CS curriculum. So I thought it was important to see it in the last lecture of CS1 to see something like this. So that's it. That's all I have for today. Don't have a lecture for Friday. I thought that on Friday what we could do is, if you want to ask questions, I'll be here for an hour to answer questions. You can ask questions about material in the class. You can ask questions about the CS curriculum or the informatics curriculum or the data science curriculum or CS&E. You can ask questions about, why should I study computer science? Pretty much ask me anything you want within reason. And I'd be glad to answer. So we'll do that on Friday. Of course, most specific questions about the exam, for example, are probably better asked on Piazza because it'll be easier for me to answer them in writing so that you have something to look at rather than having to sit here and just talk you through it. But some questions we can answer in person. I'm glad to do that. So I will see you Friday. Don't forget the homework is due Friday night. The exam is a week from Friday. People with SDS accommodations, I'll write you individually, either today or tomorrow. And I promise that I will spend part of today catching up on Piazza. I didn't get a chance to answer questions last night. So, course evaluations are open, right? You all know how to do that online. So you can take your time on Friday to do that as well. We'll see you. Thanks for a good semester.